So we're now going to talk about the structure and functionality of a Java semaphore. A Java semaphore implements a variant of counting semaphores. We've already talked about what that means. It doesn't implement any synchronization-related interfaces, unlike some of the other stuff we'll talk about later, like reentrant locks and so on. It has several constructors that can be used to create a semaphore with a given number of permits. You can see here that that's the parameter, the permit count. Now, here's something really important to understand, and it's confusing at first because it seems non-intuitive. The value that's passed in here is not a maximum value. It's just an initial value. It just gives the permit count the initial value of whatever you pass in, but you can increment it higher than that if you want. Probably not a good idea, but it's possible. And in fact, this is even weirder. The initial value to a semaphore can actually be negative. And that means that any threads that try to acquire the semaphore are going to have to block and wait until some other thread or threads increments the permit value to be positive. You can't make any progress as long as it's negative. The implementation of the semaphore class in Java applies the bridge pattern. This is a good old pattern from the Gang of Four book, as you can see here. You can read about it down there. And basically, in a nutshell, this pattern decouples an interface from its implementations so that fair and non-fair semantics can be supported uniformly. We're going to see this a lot in a lot of the core synchronizers in Java. You can have fair and unfair semantics, and I'll talk about what that means in a second. The implementation of the actual semaphore logic is done by this sync implementer hierarchy. This comes straight out of the Gang of Four pattern for the bridge. So we have this sync object. We have an object or a field of type of named sync of type sync with a capital S. And sync extends a framework that's built into Java called the Abstract Queued Synchronizer framework. We're going to see this show up a lot as well. This is a framework that's used for a bunch of things in Java where you need to have FIFO wait queues. And I think you all know what a FIFO wait queue is. It's like waiting in line at a movie theater or at the TSA checkpoint. It means first in, first out. So whoever gets there first is the first one to be serviced, and the next person is the next person, and so on and so forth. There are then a pair of subclasses that extend sync, which in turn extends abstract queued synchronizer, called non-fair sync and fair sync. And as we'll see, non-fair sync gives you non-first in, first out semantics for waiting threads, whereas fair sync guarantees first in, first out semantics. And we'll talk about how that works shortly. The constructor here can be used to enable fair versus non-fair semaphore behavior or semantics. And it's by a Boolean parameter that's passed in here. And basically, if the value of fair is true, then we make a fair sync implementation. Otherwise, if the value of fair is false, we make a non-fair implementation. And I'll explain more in a second what it means to be fair and non-fair. And this is the same type of pattern that's used in the reentrant lock class we're going to talk about later in the course. If the parameter is set to true, that means that we have strict FIFO fairness. And that means that the threads that are waiting to acquire the semaphore are guaranteed to be queued up in, first out order, so that it'll be fair. As we'll see, there's pros and cons with this. The pro is you get fairness, but the problem is it's more expensive. You have to wait in line, if you will. With non-fair semantics, in contrast, you get faster overall performance, but it's not fair anymore because a thread that's been waiting longer may not get a chance to get the semaphore when there's multiple threads that are waiting. Some other thread may kind of cut in line, if you will. The default behavior of semaphore quite correctly favors performance over fairness. You usually just want it to be fast. You don't really care about which threads get it as long as somebody gets it. But if you do care, and we will care at later points in the class, then you need to get fair semantics. Fair sync is generally a heck of a lot slower than non-fair sync, so use it accordingly. If you need fairness, by all means, go for fair sync. If you don't need fairness, then go with the default behavior. As I mentioned before, acquiring and releasing permits from and to a semaphore need not be fully bracketed. A thread that acquires a semaphore need not be the one that releases it. And we'll see that when we talk about the ping pong example here later in the next class.